I'm Karen Gundy-Burlett, the Program Manager of the NAMS-2 contract, and I would like to welcome you to today's edition of Airtime by NAMS-2, and this is a collaboration between Crown Innovations and UC Berkeley. This is a series of seminars on advanced aviation, interesting research, and innovative methodologies in AAM and air traffic management. Today's topic is the future of air mobility, agile and collaborative robot autonomy. And today's speaker, Giuseppe Loiano, is an associate professor at UC Berkeley and director of the Agile Robotics and Perception Lab. I invite you to read the speaker's biography in the notes because it is tremendous. Okay, he has a huge number of awards and honors. He's a senior editor for the IROS conference and an associate editor for many other conferences and journals on robotics. He's the chair of the IEEE RAS Robotics Foundation Cluster and the IEEE RASTC on aerial robotics and unmanned aerial systems. His work has been featured in a large number of renowned international news and magazines. And with that,
so thank you very much for the invitation. Apologize for the little problem for setting up, but we're ready to go. And today I'm gonna present a little bit what we have done in the last couple of years, especially 2 years, on agile and collaborative robot autonomy and how this fits within the future of air mobility. So really there has been a tremendous success in terms of autonomy in robotics, but even beyond robotics. If you think about 2010, people were working mainly on problems related to planning and control in really well-known environment. If you think motion capture systems or like with really simple racetrack for autonomous driving. And then in 2018, we really went into the era that I call intelligent autonomy, where we really start to bring this autonomous device in the field. Amazing videos from Skydio, for example, and also from Waymo in terms of autonomous driving. And recently, I think from 2024 onward, it's the era that I call human level performance. So we really want to reach the next level of autonomy and how the human is, behaving and thinking. And there has been lots of focus on racing. So can we push the limit of this platform? And you can see that the trend is very similar, both in ground mobility and aerial mobility. So really what we're interested in my lab is to build basically devices which are unmanned, small, agile, resilient, and collaborative. And we believe that this is going to be really the beneficial for several applications related to national security and search and rescue, agriculture, which is in need of tremendous manpower, autonomous delivery, and more in general, smart transportation. So we really see this autonomous system interconnected within city-like environment with cars and other autonomous devices. So there has been lots of progress, as I mentioned, in autonomy, but at the same time, we're still far to have reliable solution. If you see small, for example, failure of a propeller generate catastrophic effects, and then even in the DARPA sub-T, you have probably seen that even the robots are still quite slow in this kind of environment. And this problem, exponentially becomes even worse when you scale the number of vehicles. So if you have multiple agents into the environment, and that's, we've seen something in the autonomous racing or in self-driving cars, basically the entire infrastructure sort of collapses. So really the challenges that I see, needs to be resolved are in terms of efficiency. So how do we make our algorithm power efficient, agile, and working on really size, limited constraint, computationally constrained platform. How do we increase adaptability and safety? So, for example, HDR scene, low texture, inaccurate models of the environment, and most importantly, how we scale the numbers and types of robot in the environment. I know many people have been focusing on one of each axis or try to maximize, the performance of one of each axis, but really the goal is to be able to design a system that maximizes the three axes of related to adaptability and safety, scalability, and efficiency. So when we look at the design of autonomous system, mainly there are two ways of enabling autonomous robots to perform in a known environment. One is the conventional autonomy, which relies on a classic sequential paradigm. So you have the robot localized in the environment. It creates a map of the environment, then it makes a plan in that type of map, and then you basically send control commands to the platform. And on the other hand, we have what we call end-to-end sensory motor policies. These are basically neural network approximator that generate from a given sensory input directly the commands to the robot, and you can train them in different types of approach, using imitation learning, using reinforcement learning, and so on. So which one is better and which one is preferable? I would say that both of them have their strength and limitations. So on one hand, if you see the localization, mapping, planning, and control, it certainly enables collaborative design. You have multiple people working on different sub-problems, and then they come together and they merge their result. It's sort of modular and interpretable, but it's very sensitive, to errors in one of these modules, and those compounds, as soon as you go from one module to another. And then another problem is that this is low in terms of computation. So if what I call it multi-level abstraction synthesis, what I mean by that is that the same information is actually used at different level of abstractions. If you think the mapping, you need a mapping for obstacle avoidance, but the same mapping is not good for localization. So you need another type of mapping, but at the end of the day, this is still the same information, just at the different level of granularity, I would say. And then on the other hand, it's low domain expertise, it streamlines the perception to actions latency, but at the same time, it could be very task specific, and it's difficult to interpret in many conditions. But both of them, have quite several limitations to scale to multi-robot system. So the question is, how can we go beyond the traditional autonomy and maybe merge the strength of both approaches and to generate efficient, adaptable, and scalable navigation. And so the approach we took in the lab is basically, we leverage, we learn, from data, mainly models and representations, and then we use these models and representation in optimal policy or optimal decision-making algorithm with certain type of guarantees to provide actions to the robot. And we're especially interested, in representation which could sort of guarantee efficiency and safety, and that can potentially scale to multi-robot systems, so that they are lightweight enough that you can, if you have communication between the agents, you can share these representations, and that could help, resilience and reliability of your mission. So where did we start? We start to basically working on adaptive and reactive autonomy. So we start to look at the problem of adaptive dynamics and control. So what we are interested in is to basically learn this system dynamics. And so system dynamics basically just a function of the state and control input, and it's predicting, the next state of the system. And this is very important because, good dynamics gives you basically good performance and safe performance of the system. Inaccurate dynamics basically cause crashes or failures of your system. So the problem is that the dynamics are time varying and only partially observable, and this is typically the case. Some systems are very difficult to model. If you think about aerodynamics effect or vibration and all these kind of things, basically, you can reach the, first principle model can reach a given level of fidelity, but at some point they saturate, and so data could be a great alternative, to a complementary alternative to basically take into account this effect. And how we do this, in an online fashion, that's really the main challenge. So what we did basically in this work is that we sort of learned the dynamics offline. So this is basically a neural network where we learn these dynamics both using some physics priors and some basically real world data. Once we have these dynamics, we can close, the classic predictive control approach on this dynamic and basically forecasting state and control input, so state trajectories overall, right? And so the idea here is that, by comparing what you forecast in the future and what you actually obtain from your state estimator, you can basically, continuously adapt your model by adapting your neural dynamics in an online fashion. What we did is that we did even a little bit more in the sense that, you can even compute the uncertainties that are related to these neural models and use this uncertainty in the way you bias the future prediction, and so on the way you solve the optimization of your system. And so we see that, this is very helpful in case we want to, for example, we attach a payload to the robot that has never seen before, so how quickly it adapts compared to static dynamics, or in the paper we also show, for example, compared to adaptive control techniques. And we see that, the error is substantially lower, especially on the Z directions. And the other experiments we did is that how do we swap all these, we swap three propellers. So the robot has never seen these propellers, so can it quickly adapt to these new conditions in the environment? And, this is performing still better compared to the static or, even to the adaptive control case that's in the paper. And so, this certainly improves, the adaptations and reliability of your system. But, if you want to bring that into the real world, the main problem is still between that mapping and planning solution. So if you think about that, that's, sequential. It's sort of reusing the information of your localization system, because the localization system needs a kind of map, which probably 2 cohorts for the mapping. And so the idea is that can we try to eliminate this kind of blocks and go toward what we call a more reactive solution. So basically, the robot navigates in the environment, and based on what it's observing on the current view, it's able to steer the robot directly into some region that are, that are safe to avoid obstacles. And so the idea we went from this to a solution that, we simply localize, and we have a control policy that's basically, enabling still safety, but it guarantees also better agility, because you don't need to store anything compared to the old approach, basically. And so just to get to the main approach, what we did here is that basically we leverage foundation models to generate depth maps in the environment. This generates a depth map which is very accurate, but it's not scaled. And so we scale this depth map using, the scale information that's coming from, several depth map or other sources of information from, for example, in this case, we're using a D455, so it comes out for free because it's still on device, the depth map that's provided. But as you can see, this one is the foundation model, the one on top. The one on the bottom left is what a classic, stereo camera device is giving you, doing a simple block matching approach. That's the D455 output. So it's an industrial grade technology. And you can see that despite the depth is scaled, there are lots of inaccuracies. So there are lots of holes in that approach. So in this case, we combine the best of both solutions. So we have a foundation model that gives us a depth, and then we rescale this depth with information that's coming from the stereo sensors. And you can see that here, you can see that on the bottom right, the projected completed depth, how accurate it is compared to the top one, which is the sensor depth from the D455, which is full of noise and inaccuracy, I would say. At this point, we have this great representation, which gives us, information about how distant the objects are in the environment. And rather than building a map using these representations, what we do is that we estimate collision probabilities. So given the current view, can we try to estimate, which object or which point in the environment are the most critical in terms of safety and reliability, and use this information directly at the control level. And so what we do here is that we basically use these points, and we compute the time to collisions to this most critical point. And then in the same model predictive control that we used before, what we do is that we add directly those points as a constraint within the system, so within the optimization, so it's becoming a control barrier function constraint. And so what we do is that, the mapping is directly part of the control problem. So we basically can just, this will have the behavior of looking at the, the collision point that are most critical and generate a safe path just using model predictive control without any explicit mapping of the environment. And so you can see that this generates quite very nice trajectories, in the environment. So I'm just telling the robot, go from A to B, from one side of the room to the other. And it just uses the current depth map to steer the robot from the starting location to the end location. This is different illumination to show that that type of representation is actually very good for what we are trying to achieve. And we also tested, in outdoor, these are some results just to show that we avoid the obstacles. And these are some outdoor environment. For example, we do some pole dodging. And then in addition to that, we also fly to some of the trees in the environment. And so really what's happening on board is that the robot is simply, computing these collision points and using these collision points in an MPC to optimally select the control actions for your robot. So definitely, we reduce the mapping, we reduce the planning. Everything is basically incorporated in a reactive fashions within an NMPC. But the real problem is that we still have some kind of external localization, which could be coming, from the Python, from GPS, or from visual inertial odometry, whatever you want to use. And so the idea is that can we eliminate this kind of global localizations and go toward a solution that's, it's more toward a human or, another more human would do, basically. We navigate with respect, to environment notions like object or rooms and so on, right? So the idea here is that, we want to go from a solution that's like on the left, which has global localization, to a solution which is, object-based. So you have a dictionary of objects, and maybe you are interested to navigate with respect to this type of, to the object you have in your memory, and then switch from one to the other according to the, your need. And so what we do here is that we extend the previous system, basically incorporating the object. So the system is exactly the same. So we have model predictive control, collision probabilities, but this time we avoid global localization. We get our reference with respect to an object in the environment, and then we track that specific objects, and we basically avoid obstacles using the previous techniques that I've shown you. And so this has given, some very interesting results in loitering, and then, for example, identifying object. In this case, it was a car, but it can be anything. It's the approach, doesn't really rely on a specific detector. You can use your own. This is, for example, tracking a human on top of a little cart in indoor-outdoor transitions, and you see there is a distractor on the right side, and despite that there is a distractor, it's still able to track the specific human. This is, the testing obstacle avoidance. The robot is supposed to go against the fence, but it goes down and still track the human that's on the little car. This is in the forest, for example, same kind of approach. And this is, probably are familiar with the DARPA Racer car. So this is the DARPA Racer car tracking in the wild at 80 kilometers an hour. So it's really lightweight, it's computationally efficient, run on boards over 100 hertz, and it's very lightweight. This is another car, just for example, to show that we can switch even types of cars. It's not really tracking a specific car object. This is another view from the top where we track these vehicles. And then these are some forest experiments. You can see here that on the bottom right, these are the collision probabilities that shows the vehicle, inform the vehicle where to be careful and where to use. And you see it's mostly on the ground, on the trees, and so those are used to basically steer the robot from right, left, and so on. And this is similar, except that at the end we also localize a human at the end of this mission. And this is showing that we can do this dynamically. So we track, the vehicle starts, and we can start tracking continuously, basically. So that's the overall idea. And this is the mission I was mentioning. I'm just going to go through. You see that at the end, we just do the same thing, but there is a human, and we identify the human in the field. If we want to, so our goal now was to, we solve this an NPC with, maybe we can learn the dynamics, we can reduce basically the perception to actions pipeline. But the reality is that if we want to go that small, maybe this optimization won't fully run on embedded devices. So what we are trying to do here is that we try to approximate this optimization with a neural network policy that would potentially run on chip. And so in this recent work, we have started this. I'm just going to briefly mention, led by one of my students, to directly incorporate the control policy on the autopilot. So this was the idea. Here we propose an actor-critic approach, RL approach. And the way we did this, we propose some curriculum learning and other stuff that make the training efficient. But really the key has been to use this self-contained library, which is called RL tools, which is used, for continuous control in and reinforcement learning, basically. And this has shown that you can train, potentially even on the small microcontroller. You can even, you don't do it, but you could potentially use the microcontroller to train your algorithm. So it's extremely lightweight, and then it's several order of magnitude faster compared to existing, solution. And so this has enabled us to basically just install our library on any type of autopilot. We're not really constrained to any of those, and basically fly with this kind of, solution. And so this, you can see that, for example, we train in 18 seconds and we're able to have a control policy that stabilizes the quad rotors, not only in hover, but it's also able to track trajectories. And more recently, this work has culminated in an adaptive policy. So what I've shown you at the beginning with model predictive control, now it has been done in a model-free fashion with a neural network approximator, basically. So you can adapt to a wide range of platform, wide range of autopilot. You can even change the configuration of the robot, as you will see before. And this is enabled, not only by the algorithm, but also by the ability to, through our library, code this algorithm directly onto any type of autopilot, because the library doesn't have any external dependency. So it's completely self-contained. This is a soft drone, which was also, tested in this kind of environment, but the most, impressive results have been with the disease when he was flying a drone, and then he's switching the same experiment that I showed you at the beginning, switching propellers, and tries to do the same thing. So, and the policy is learning and adapting online. Particularly impressive was, when we had this kind of disturbances that go beyond 90 degrees roll and pitch, and the robot was still able to recover and adapt. And this is completely open source, so anyone could potentially reuse it for their own project. So next step on this is that how we extend this to basically visual input, similar to what we have done in the other case. So you get visual input. Can you get your policy rather than from state informations directly from visual observation? So that's what we are aiming to achieve. And also we're trying to extend this, some of this concept to fixed wing. So we're doing lots of work related to improving energy harvesting from the environment, mainly through soaring capabilities. So we're really interested, in using some of these, model predictive control, but also learning-based framework to enhance the capability of this system. So this is an active project we're actually working on with the government. Another area that could be very interesting, especially for fixed wing, because it's very hard to do the sort of reactive collision avoidance, or you can have it, but it should be complementary to high range navigations. And in case of high range navigation, you need a sort of localization system that is beyond the GPS. And so what we're doing here is that we're doing a lot of thermal geolocalization. So we use either RGB or thermal information and match this information with satellite data to basically enable global localization, even in without having GPS. And this has been tested, in a wide range of environment, including desert-like scenes, which are very self-similar and so on. So if you're interested in this area, we have also some software that's been released that will be more than happy if you use it. And then in the last part of the talk, what I'm gonna discuss is how we extend these models and representation to multi-agent systems. So where does it make sense? What do we share, and how this improves basically your overall mission? And so we are really interested in in seamless algorithms that are able to collect in a seamless manner and fuse intermittent distributed data for accurate and resilient context-aware decision making. And so in this case, we're interested in two main problems. One is the planning problem under limited communication constraint, and the other is how do we collaborate in terms of perception capabilities between multiple agents. So to give you a quick understanding on how this works, basically, we should imagine that we have a network of robots. Each robot has its own sensor input. For example, in case of collaborative perception, it's an image. In case it's a control policy, it might be an image or might be the state of the robot, whatever you like. But for example, we assume that in this case, it's an image. And so what we use here is that, in terms of output, you would like, for example, to have depth estimation from each robot viewpoint, or semantic segmentation, or other type of, high-level perceptual information that could be useful for, robot reasoning, I would say. And here what we do is that we use graph neural representations. So each robot basically encodes the informations. There is this distributed neural network, which is called graph neural network. We share the compressed information of each robot with the neighbors if there is communication. So we do multiple rounds of communication in the intermediate phase in case communication is available. then each agent collects the information that has potentially received from its neighbor and merge it with its own information. And then it's decoding this information into the task-dependent information. In this case, the task was to get a depth, but you can get semantic segmentation and so on. So the idea here is that, this could be useful in case one of the agents, for example, is affected by sensor noise or by an adversarial attack or by, some kind of, I would say attack from an external environment to basically still fulfill its own mission, right? Still fulfill the ability to reconstruct the depth from its viewpoint, or still the ability to do semantic segmentation from its own viewpoint. And so here we have just, in the process of releasing this framework where we can consider multiple agents, in this case with cameras, but this is good also if you want to, do control policy and collaborative control policies and so on, to produce, collaborative perception capabilities. And in this case, we focus on depth estimation and semantic segmentation. So you can see that, for example, in this case, even if we have 2 aerial and 1 ground robot, even if all the robots have healthy inputs, the ability to share information reduce the uncertainty, for example, of the depth information, right? So that's one way to see also the benefit of this collaborative approach. The other benefit, for example, if you have occlusions, like in if you have occlusion, like in this case, the chair is occluded by a table, the collaborative perception enabled the detection of the chair from the ground robot viewpoint. But this is a framework that you can use also for collaborative planning and control. And this has been a big project that we have also tried to release a data set in the wild, because there is lots of data for autonomous driving, but the context of robotics is very different. You have multiple types of mobility, you have multimodal sensing, and so how do you? We released this data set with 4 robots and the mix of aerial and ground robot. And to show you a little bit, what I was speaking before, for example, in this case, the Agile robot number 1 has a completely noisy input. In principle, it's supposed to reconstruct what you see here at the, at the top, that I circled, that's the ground truth, that's the second column. And so, but on its own, the robot is not able to reconstruct anything once it has that input. But if you share information with a different agent, at least the robot is able to partially reconstruct, the view of the environment and reconstruct the depth of the environment. So it's sort of helping in the reconstruction process. Similarly, we are interested in multi-robot planning problem, similar approach, but under limited communication. And here we use an hybrid solution. So we use the same neural network structure to having multiple agents collaborating with each other, and that guarantees scalability. So in terms of number of agents, and then we couple that with the model predictive control with the second order control barrier function to guarantee safe navigation and obstacle avoidance. So this tries to merge the benefit of the 2 approach. One is on the end scalability, and the other is the safety of execution of the motion for each one of the agent. And we got very interesting results here, where you can see that if you go here, the red dots are actually generated by the neural network. So this is a task assignment problem where you need to decide which robot goes to which goal under limited or intermittent communication, right? Optimal solution exists in case of fully connected layer, and there is also the optimal algorithm, so you can train this offline and deploy distributed, I would say. And we can generate intermediate goal. You can see also from this graph neural network, and this works both in case of free space, but also in case of objects in the environment. And we have also an analysis, theoretical analysis of what kind of detection range, which could be communication or perception you need to guarantee basically that the algorithm gives you safe results. And we also showed this, in the field with ground vehicle, how they go from starting to goal location with limited communication. We have also quite a bit of work on physical collaboration as well. Here, the goal is to, move toward a system that, for example, in this case, have also manipulation capabilities, manipulation transportation capabilities. So similar to the previous approach, we have control policy for this kind of hybrid system on the left, which switches from taut to slack cable. And then on the right side, you see, for example, the case of, I call the future of warehouse automation or constructions. It's where, you have really large load that needs to be transported by a set of robots, and this could help a human to accomplish this task in a very easy way. So the idea here is that the structure is completely compliant to the user interactions, and we're also able to estimate the user forces without any force sensors on the structure, just looking at the motor values of the vehicle. And the other great thing is that this system has some redundancy, so you can basically move the robot for achieving, for example, safety or other type of task, while without penalizing the trajectory of the load or the interactions from the human. So a few takeaways, agile and robust flight emerges when autonomy is adaptive, reactive, and grounded in what the robot can observe. I've shown a little bit, how models and representations can be exploited for safe, adaptable, and scalable navigations. Physics knowledge is certainly something that we've seen beneficial, especially when we learn these models. And collaboration definitely improves resilience to failure and mitigate adversarial attack. So, of course, there are several limitations. If you think about the robot autonomy framework we've shown, it has only local safety guarantees. It's has not yet semantic reasoning. So potentially, you can combine with visual language models. In terms of collective intelligence, right now the framework, it's mainly task and robot dependent. We also showed only homogeneous type of sensor, in the sense they have only cameras. What we're really interested in and we're working on is multimodal sensor. So the ground robot has a LiDAR and the aerial robot has a camera. So can you do the same task with this diversity of information, with information that complement each other? So that's the overall idea. And can you share just relevant information? So right now we mainly share the full image, but the reality is that you can share information based on the type of task you have, but also on the type of mobility that the robot provides. If you are a ground robot and you are an aerial robot, your information you want to share might be different just because you are moving differently. So your range of actions are potentially, affecting the type of information that is beneficial to your neighbor. So there is a lot to understand in this area. To give you a little bit more ground on what currently we're working on, so we're very interested, in word models. So, for example, for the first part where we learn dynamics, we would like to learn latent representations of the system and directly plan and control in the latent space. So this would enable to basically further scale down computation, compress information, and give really the context to the robot. So you can imagine that you have a view of the scene and you want to navigate just using images to get to a goal. So the idea would be that you don't estimate any more future states, but your future states is literally the image. So what you're going to forecast is going to be future images. And so we have already some results on that as well, but that's a very exciting, direction, especially on how then you guarantee safety. And what's the relationship between the motion in the latent space and motion in 3D. And then how do you extend this to multi-agent system? I think, the way I see it is that each one of these agents is basically as a neural information, or it's a neural agent, I would say. And this neural agent can either have representation and use this representation, coming from, the specific task you are trying to solve, or it has basically a model like the one on top right? So you can imagine that each one of these word model is within one of the agents. So the question is, how do you extend this to collaborative settings? So you condition your model not only to the input of your own agents, but also to the information or observation that are coming from the other agents. So this will become a collaborative word model, and then you can do collaborative predictive planning and control. If you think about it, for example, you can do a distributed MPC working on the images, or all this kind of stuff. And the idea of this word model, the other benefit is that you could fuse heterogeneous information. So it's compressing everything. So you can potentially give LiDAR images or state space representations, and that gets everything compressed into that specific representation that is using. There is the question of then what to share and when to share. And this I already mentioned, distributed foundation model. And then there is also an area of real to sim. We have lots of real world data. How can you feed that back into simulator to further improve the system? And actually, a few weeks ago, another DARPA program came out it's called CypherForge, which is actually looking at this loop of continuous improvement for 5 aircraft, basically. Also, the platform we use, mostly done by us with US component. We do everything in the lab. We don't buy anything out. I mean, we buy component outside, but we assemble everything in the lab. And we also have a new flying space that I invite you to visit. It's very nice in Berkeley with 30 Vicon cameras, and we have lots of outdoor space. I want to thank you all, the students and sponsors, and I'm happy to get questions. Thank you. Yes, should I stop sharing? Okay.
Are there questions online?
Maybe there is on the chat or something. Oh, we're sitting up.
I can go.
Yeah, please.
Yeah, it's more like a comment. Very nice talk, very impressive. I really enjoyed listening to the talk. Just want to say that I'm working on a project called ACERO. The project is looking at how we can bring advanced capability into the wildfire response, especially UAS.
And then we're looking, right now we share the full compressed image. So we share the latent representation of the image. Is it really useful that you share the latent representation of the image? Probably not, because if your task is just to detect, I don't know, do object detections, maybe you want to share some information that's already relevant to your task. And then you want to share it based also on your motion capability. So that's what we are very interested in. If you are a ground robot, you can only move in certain type of direction due to your, autonomy constraint and so on. And similar, the aerial robot is starting from another viewpoint that moves way differently than the ground robot. So how can your motion be beneficial to the information sharing? That's the questions we are looking for. And the idea is that, maybe you can use your model to do some kind of forecasting future predictions on where you're going to be in the future. And if that's useful, that you share some information with the other agents. So that's the three aspects we're looking into right now, related to the collaborative perception task.
And the way you're adjusting the velocity of drones is based on the reinforcement learning, because like it has some latency to
So
optimize.
right now, the task of perception is purely high-level perception. So we don't do anything related to the control yet. So these are two separate areas. One we do the perception, other we do the control. The ideal case would be that you merge with the future work that I mentioned, where you have this collaborative world model, where you have perception information, you can reason over a long horizon with this perception information from any agent viewpoint, basically. So that's the overall idea. We see there the combination of merging the two things together, because the model of each robot will be conditioned to the input to its own input, but also to observation that are coming from other agents in the environment. I see that as an extended version of a Kalman filter or multi-agent Kalman filter, except that you have changed the domain of the representation domain, which becomes your full compressed observation space at that point.
Yes, thank you.
Thank you. Great.
Actually, there's a question. Michael, do you have a question?
Yes. Can you hear me?
Yes.
Yes.
Yeah, I had a problem with my connection. But, anyway, so that's really cool. But I'm curious, how is it related to what we use in traditional aviation, and not only in traditional aviation, but in UAM applications, to define the trajectory of aircraft, if we are talking about the flying drones, for instance. So we usually provide something like flight plan or intent as a sequence of waypoints or constraints to define the desired aircraft trajectory. And you define the high-level goals of your missions, and when you are translating it into this specific policies or guidance, are you using something similar at some stage, or are you skipping this altogether?
Yes, that's a great question, and that's exactly what we are doing right now in the soaring project. So the mission comes from high-level specification, which is the user or high-level, for example, weather maps that you can get online. So you have a sort of global planner which basically design your initial missions in the environment. Now, of course, you need to translate these high-level missions into low-level control command. So the way we're approaching this is that this is, the high-level mission specifies in this global planner, and then at the local level, we're actually, using these predictive planning and control techniques to execute this kind of mission at a different level of, at the more, not at the coerced level of the original global planner, but more on the, in a shorter time and spatial range, using the onboard sensors of the platform. For example, airspeed sensors, you may have radar, or you may have, even a small, wind sensors on your robot, or even thermal camera. For example, if you want to detect the presence of thermals or not in the environment to improve the overall time navigation, so to improve the endurance of the platform. But really, the way we're doing this is that once we identify it, we basically recently are running model predictive control to basically translate high-level commands into low-level specifications for our platform, basically.
Thank you.
Well, I'm afraid we're running out of time here.
Thank you very
I
much.
want to thank you so
Thank
very
you
much.
very much.
Really
Thank you.
outstanding.
Thank you.
So next week's speaker will be Dr. Mark Mueller from UC Berkeley, and his title will be on the subject of controlling and motion planning for redundancy and safety. Anyway, thank you all very much.
Thank you.